Today's section is on section 8.5, write and graph exponential growth functions. So far in this chapter, we've dealt a lot with exponents and how to simplify them in problems and evaluate. But now these last two sections in this chapter, chapter 8, do something a little different. They introduce 8th graders to a new type of equation we haven't seen much of before. And I'll show us a few examples of that. Mainly 8th graders, we've just dealt with linear equations, linear functions, how to graph those, make those. But another type we're going to deal with now are exponential. There's exponential growth, and then there's exponential decay, which we'll talk about in the next section. But exponential growth, what do these look like? Okay, well, first, just a reminder. Here's a couple scatter plots that have linear patterns to them. Remember, a linear pattern is something that makes a straight line graph. So just showing a couple of those examples, linear patterns. We've dealt with these before. But now there are other types of patterns out there that we can model. Here's an example of an exponential graph, or something that follows an exponential pattern. It's actually the world population. So again, something very, that we are involved in. The world population, as time goes on, you can see from the 1300s to the 1400s to the 15s to the 16s and so on. Okay, the pattern has been fairly flat, but then as soon as we got to the 1900s, these 100 years right here, well, the population increased very, very dramatically. This is what an exponential function does, or any kind of exponential relationship. It grows kind of slowly at the beginning, but then it'll grow very fast once it hits a certain point. Here's a couple other examples of those too. A few I'll talk about in class. Cell phones. Cell phone subscribers. Again, when cell phones first came out, there were not a lot of them. Not a lot of people involved in cell phones or had a cell phone. But then as they became more and more popular, more people had them, well, then the popularity increased dramatically, very, very fast. So most technologies do something like that as well. And sometimes even money, when you invest money, that's something that can also follow some kind of exponential relationship. So just kind of a few examples of what we're getting into, relationships that look like that in the graph. And again, we'll talk about how we can figure those out here on this first page. So here on this page, I've got some kind of key points for both linear and exponential equations. And I know this stuff isn't in red right now, but this is stuff, if you're taking notes along with me, I would like you to write down, make a chart like this, linear equations, and then the bullet points that I've got right here. And same thing for exponential. And I want to compare the two, because when I'm talking about exponential equations, it'll still help to remember things about how we make a linear equation as well and how those are graphed, because there are still some very, very close similarities that will help us kind of understand how the numbers fit together in an exponential equation as well. First, just a few things to remember though. A linear graph is a straight line graph, as I showed in some of those examples. X is a base in the equation, right? It's not a number that's in an exponent or in the denominator or anything. It's just some kind of number that's in the equation. Again, it'd be a base. It'd have a power of 1, I guess, if it was in the problem, if we wrote that in. But it's a base number in the equation. And our general form, y equals mx plus b, that's how we often write our equations. So something like, again, y equals 2x plus 3. There'd be an equation in linear form. We've made tables for linear equations. We've graphed them. And even if I have a table, I can make what the equation is. So going down to this example right here, we can make an equation just knowing all the numbers in this table for some kind of linear equation. Again, it would look like this, y equals mx plus b. What I'll look for usually is some kind of pattern going on. As x increases by 1 every time, what's happening in my pattern with my y coordinates? Well, it looks like it's going up by 2 every time. That's kind of our rate of change, our increase. So remember, that's usually what our slope is then in these kind of problems. Our slope will be 2. And my b, my y-intercept, well, that's when I've plugged in 0 for x. That's like kind of like my initial amount. Sometimes too, if it's a word problem, like where I begin. So in this case, about a y-intercept also on my graph, it's where x would be 0. So that'll be this point right here, so 0, 8. So my y-intercept would be 8. So for this equation, I can make this, the equation that would model this table be y equals 2x plus 8. Again, reminding us all of these linear things, because exponentials, there's similar things that we can do. Find some kind of pattern and be able to make the equation. Looking at what's important to know about exponential equations. Again, for linear equations, we have a straight line graph. For exponentials, as I showed some of those examples, we're going to have some kind of curved line. So and again, something that usually, and we're talking about exponential growth, something that will increase very rapidly as it gets to a certain point. X is in the equation as an exponent in an exponential equation. That's why it's called exponential. X will show up, but it'll be as an exponent in the problem. So as you can see right here, here's what it might look like. Something like y equals a times b to the x power. That's kind of our general form for an exponential equation. A times b to the x power. Now, just like I talked about over here with linear equations, y equals mx plus b. We had important things that m and b stood for that could help us maybe figure out what this equation might be if I was given a table or some kind of graph. Like if I could find these important numbers, whatever the pattern may be, or the slope of the line, or the y-intercept, then I could make the equation. The same thing is going to happen over here. A and B are both important numbers that there's a way I can figure out those two numbers and make an exponential equation. One of them kind of acts like the slope, and one kind of acts like my y-intercept or like a beginning amount, as we'll find out here. So in this table as well, this one I'm telling you models some kind of exponential relationship. We'll still look for some kind of pattern in this table if I'm going to try to make the equation for it, y equals a times b to the x power. Well, if I'm looking for some kind of pattern, again, I'm seeing that we're going up by 1 every time in the x coordinates, so that's good. As I go up by 1 every time in the x coordinates, what's happening with my y coordinates? Well, let's do something a little different, right? In the linear pattern, we noticed that it was adding 2 every time. But if I look at this in my my exponential pattern, well, it's something different. In this case, it looks like it's multiplying by 2, right? It's not even adding the same amount every time, from 1 to 2, 2 to 4, 4 to 8. So it's not adding the same thing every time. In this case, it's actually multiplying. It's doubling every time I go up by 1 in my x coordinate. Well, how does that happen? In an exponential equation, that's actually going to show up as my b here. Okay, actually I'm gonna make this a little bigger for us. Okay, but here's my general form of the equation. This b, this variable here, stands for the growth factor when I'm talking about an exponential equation. And in this case, this is the growth factor. Oops, if I can spell it right, factor. But that's b is going to be the growth factor. So what is it? Kind of like slope acted like in my linear equation, right? It was going up by 2 every time. We talked about things like that. What's it increasing by? But in that case, it was adding every time. It was adding 2, adding 2, adding 2 in my table. Well, in the exponential equation, again, it grows a little faster once it gets going. So in this case, now it's multiplying by 2. So it's still kind of like a growth factor, but this is where that shows up, this term right here. So far, this equation will look like y equals a, which is some number, I don't know how to find that yet, times 2 to the x power. Because it's multiplying by 2 every time, here's where that shows up in an exponential equation. By putting some new exponent for x all the time. But if I want to show that it's doubling, my 2 will actually be the base number there. That will keep my numbers doubling every time as this table is showing, that kind of pattern. A then, again, a in my exponential equation is just like another thing in the linears. Again, trying to compare these two so you can see. We used to have something like a y-intercept, correct? That was like an initial amount or someplace that we started, or when I put in 0 for x. Same thing is going to happen for this a in an exponential equation. It's like my y-intercept, really. It's when I put 0 in for x, what do I end up getting for a result? I end up getting 2. This is kind of like, sometimes I'll call, you can call it your, you can still call this your y-intercept. It's also, as we'll find in many word problems, it'll often be like an initial amount that we're starting with. So we'll think of it like that too, and kind of both of those terms. A is usually like a beginning amount, something we're starting with, or again, you can think of it, it's like the y-intercept in this case for an exponential. That a is going to be our, when we plug in 0 for x, that's going to be our y-intercept, just like in a linear equation. So that number that we get, that's going to be our a. So in this case, this also ends up being 2 for this particular problem. So the equation that models this table is y equals 2 times, well, 2 to the x power. We'll then go through a few examples here in class just to make sure we get this idea how I can make some kind of exponential equation. Again, here's the general form, and like we were just talking about, this is going to be that A is going to be like my y-intercept. If I was graphing these, that'd be like my y-intercept, and B is my growth factor. Again, for linear equations, we had talked about maybe a slope. But in exponential equations, again, call it a growth factor. Again, still a way of increasing how the numbers are increasing in this case, but they're multiplying by to get to the next number in my table. So we call that the growth factor. So if I'm going to look at, maybe the directions might say something like write a rule for this function, model by this table. Well, I can see in this case, again, my x coordinates are increasing by 1. So I'll look for some kind of pattern in the y coordinates. This one also, again, looks like it's going from 1 to 2, 2 to 4, 4 to 8, 8 to 16. It's doubling every time. So my growth factor, my b is going to be 2. And my a, again, is my y-intercept. That's when I plug in 0. So my a is going to be 4. So this equation would be y equals 4 times 2 to the x power. Looking at that next one, same kind of idea here. I see again that x is going up by 1 every time. That's good. I want to make sure that's consistent as well, just to make sure that checks out. As that's happening, what's happening in this case in my y coordinates? Well, it's a little tougher to tell in this one, just because I got some fractions going on there, but maybe you can even still figure it out from 1/8 to 1/4, 1/4 to a half to 1, 1 to 2. You could think, what if this pattern kept going too also? Or maybe look at some of these bigger numbers, knowing it's an exponential. This one is also just doubling. So this one also, my growth factor, again, I made a bunch of examples like this so far, but the growth factor is just 2. What's my y-intercept for this one? Looks like if I put in 0, I got 1/2. So that's going to be my initial amount, or my y-intercept. So this one's going to be y equals 1/2 times 2 to the x power. Just quickly going through a couple examples just to make sure you understand that not every growth factor is always 2, so that I can make some other ones as well. This next one, x is increasing by 1 every time, so that's good to see. Well, what's happening in the y coordinates? Again, this one, sometimes if you get some fractions in your table, it's a little tougher to tell at this point maybe what's going on. So concentrate maybe more on the integer numbers you have here, the ones without decimals. Well, if I go from -3 to -15 to -75, what's happening? Well, 3 to 15, looks like I'm multiplying by 5. So that's my growth factor for this one. And my initial amount, well, that's when or my y-intercept, when I plug in 0, I got -3. So 0. So a has got to be -3 for this one. And so if I know a is -3 and b is 5, I can say y equals -3 times 5 to the x power. And obviously I do notice that all my numbers are negative. Well, that makes sense because -3 is my number here. Every time I'm always multiplying by a negative, whatever I find my power to be in this problem. Once I evaluate this part, well, then I times it by a negative number. So that's how all those numbers end up being negative, because it is -3 in front there. That does make sense. Y equals -3 times 5 to the x power. One more here. This next one looks like, well, I'm going up by 1 every time in x. So good, that's still consistent. If I look at these fractions, 7/9, 7/3, now I got 7, 21, 63, aha. As I look at some of these last ones, looking for the growth factor there, it looks like those are some common ones. I'm multiplying by 3 every time, right? And I would find that down here as well. Yep, that's what's happening. I'm multiplying by 3. Then if I look for my y-intercept, when I plug in 0, I got 7, so a equals 7. So for this one, y equals 7 times 3 to the x power. Last thing to talk about these is how do you graph one of these exponential equations. Again, I showed you a few examples at the very beginning, so we kind of know what they look like. But to graph them, the best way right now, I'm just going to ask you to plug in some points, find some ordered pairs, find some solutions for the equation, plot those, and make the best graph you can. I'm not expecting them to be perfect because this is the first time we're trying it. But finding some ordered pairs, that method is still one of the good old standby methods that we can use. So in this case, they give me some x values to plug in, -2, -1, 0, 1, and 2. So I'll show you how this looks like. Well, what am I going to do? Let's start off with kind of an easy one here. We'll plug in 0 and see what we get. And we should kind of know, maybe even thinking about those table ones we just did. If I plug in 0, what happens? Well, I have 2 times 3 to the 0 power, Remember, what is anything to the 0 power? If I evaluate this part right here, anything to the 0 power is just 1. So in this case, this just means really 2 times 1, which is just 2. So if I put in 0, I get 2. But remember, that makes sense kind of, right? Because remember, there's that A, that number that I have in place for A, that's like my y-intercept. So whenever I see that number anyway, I know that's going to be, when I plug in 0, that's what I'm going to get. In this case, I'm going to get 2, or whatever that number happens to be. So good, that makes sense. I put 0 in, I get 2. I'm going to put some other number in here. Let's say now we put in 1. Well, 3 to the first power is just 3. Times 2 would give me 6. And if I put in 2, just kind of writing it in here to give a little visual for myself. 3 squared is 9. 9 times 2 gives me 18. Thinking back to what we learned in the table, right? What kind of pattern do I see here right now? 2 to 6, 6 to 18. It's multiplying by 3, right? That makes sense. That's my growth factor, so that should make sense that that's what I'm getting. Okay, I can kind of double check like that, but yep, my numbers make sense so far. Okay. Well, now what happens, and we should kind of know this, or remember this from earlier in this chapter. Now I'll go back to these last two here, these first two that I've got in the table, I should say. What happens when I put in -1? Well, we learned what happens when you put a negative exponent in, correct? It's kind of like take the reciprocal of that number, so this is really like 2 times, well, now it's like 1/3. And 2 times 1/3, well, that's just 2 over 3, or 2/3. So that's what I get then when I put in -1. I end up getting a fraction. Again, that you can punch in your calculator to help you too. I'm okay if you use your calculator to help you on these. But that's what I should end up getting. What if I put in -2? Again, we should kind of know that too. You can use your calculator, but I can show you how it works here again just as a reminder. If I put it to the 3 to the -2nd power, it's going to be like 1 over 3 squared, right? Once I put it back in the denominator, it becomes a positive exponent. And 1 over 3 squared, that's just like 1 over 9. So this is really like 2 times 1 over 9, which would be like 2/9. So now I got 2/9 here. When you're graphing these, here's what you're going to notice for many of them. They're gonna start out they're gonna start out kind of tiny. Again, they start out growing very slowly, but then all of a sudden they'll hit a certain point. The exponential growth kind of shoots northward pretty quick. So -2, 2/9. Well, it's kind of hard to plot 2/9, but just make your best guess. You know it's gonna be somewhere kind of close here. So right there about -2, 2/9. -2, 1/3, maybe right about there somewhere. 0, 2. Now these are sometimes I should be able to plot better. 0, 2, 1, 6. That's going to be right about up here. And then again, 2/18. Now that's going to start maybe going off your grid already or getting pretty high up there. So do the best you can on 2/18. I'll be kind of understanding on one like this. Should be somewhere right about up there though. Okay. And so here's what these are going to look like, right? Again, like the examples you saw, they start out growing very slowly, but then once they hit a point, all of a sudden they start growing very fast. So the linear graphs will look something like that. Okay, and I would make a table, just like we saw here, make a table, and then some kind of graph. Also on these homework assignments, I typically let you do 2 graphs on 1 grid, so just kind of save some room. So let's say this is problem number 1, and then you got to graph problem number 2, maybe it looks something like this instead. So I'm okay if you put a couple problems on each grid. That'll always be okay with me when we're graphing in this section, just to save a little space.